Have you ever looked up at the night sky and wondered what's out there? It's a big question, a really big one. We see stars, planets, and galaxies all spinning in the vast dark expanse. But here's another question, maybe an even more important one. What do you see when you look back at Earth from space? For decades, we've been sending astronauts and satellites into orbit. They get this amazing, breathtaking view. They see our home, a beautiful, swirling blue marble hanging in the blackness. And from that unique vantage point, they see something else. They see change. They see our world changing right before their very, very high up eyes. This cosmic perspective is everything. It's what changed our whole understanding of our planet. Think about when you go to the doctor for a checkup. The doctor measures your temperature, checks your blood pressure, listens to your heart. They gather all this information, all this data, to see how you're doing. That's exactly what we're doing for our planet. Our doctor's office is in space. We have hundreds of satellites orbiting Earth right now. They are our planet's thermometers. They are our stethoscopes. They are our blood pressure cuffs. They are constantly taking Earth's vital signs, giving us the most comprehensive health checkup in history. It's a planetary physical exam. These satellites are equipped with amazing instruments, not just pictures. The pictures are spectacular. They measure things our eyes can't see. Sensors measure ocean temperature down to a fraction of a degree. They measure sea level height with incredible precision. They track polar ice, watching it shrink over time. They are our planetary diagnosticians, collecting the evidence to understand climate systems. This data is absolutely critical. Without it, climate change would be just an idea, a theory. With information beamed from these orbital sentinels, it becomes fact, backed by mountains of evidence. Let's talk about some of these amazing space missions. They have names that sound like they're from science fiction, but their work is very, very real. Take the Landsat program, for example. This is a joint mission between NASA and the U.S. Geological Survey. The first Landsat satellite was launched way back in 1972. For over 50 years, Landsat has been taking pictures of Earth's land surfaces. It has created the longest continuous record of our planet's landscape from space. Think of it as Earth's family photo album, showing us how things have changed over generations. What does Landsat show us? Deforestation in the Amazon rainforest, our cities growing and sprawling outward, lakes like the Aral Sea shrinking to a fraction of their former size. These aren't just pretty pictures, they are visual evidence of our impact. By comparing images from the 1970s to today, we can literally see the changes. Then there are missions like Terra and Aqua. Terra launched in 1999 and crosses the equator in the morning. Aqua launched in 2002 and crosses the equator in the afternoon. Together, they give us a daily snapshot of the entire planet. They measure clouds. They measure aerosols. They measure the planet's energy balance, how much sun energy comes in versus how much goes out. And we can't forget the weather satellites. Missions like the GOES series hover over one spot and provide continuous updates. They make local forecasts far more accurate. They track hurricanes as they form, giving us precious days to prepare and evacuate. Now, let's zoom in on two of the most critical parts of our climate system, the ice, the oceans. These are like the planet's air conditioning system, and they are changing fast. To study them, we need some very specialized detectives in space. One of the coolest missions, pun intended, was called ICESat, and its successor ICESat-2. Its job is simple but incredibly difficult, to measure the height of Earth's ice sheets with mind-boggling precision. Greenland, Antarctica. It's so precise it can detect changes in ice thickness of about the width of a pencil. How does it do this? ICESat-2 uses a laser, a very, very fancy laser. It shoots 6 beams of green light down to Earth. The satellite's instruments measure the tiny amount of time it takes for those photons of light to travel down to the ice, bounce off, and return to the satellite. By doing this over and over, it creates an incredibly detailed three-dimensional map of the ice. By comparing maps from different years, scientists can see exactly where the ice is getting thinner and how fast it's melting. This data is vital for predicting how much sea levels will rise in the future. ICESat-2 is our frontline reporter from the frozen ends of the Earth. Of course, melting ice has to go somewhere, and that somewhere is the ocean. For that, we have missions like the Jason series of satellites. When we invest in space exploration, we're usually aiming for the stars. We want to explore Mars, study distant galaxies. But along the way, we invent all sorts of amazing technologies to make those missions possible. Many of those inventions turn out to be incredibly useful right here on Earth. Take solar panels, for instance. The very first satellites needed a way to power themselves way up there in orbit. You can't exactly run an extension cord into space. So scientists and engineers perfected the photovoltaic cell, the technology that turns sunlight directly into electricity. Early solar panels were incredibly expensive and not very efficient, but they worked. Over decades of development for the space program, they became more efficient, more durable, and much, much cheaper. On the International Space Station, every drop of water is precious. So, NASA had to develop advanced water filtration and purification systems that could recycle everything, and I mean everything, sweat, urine, back into pure, clean drinking water. That same technology is now being used on Earth in places that lack access to clean water. Astronauts on long missions to Mars will need to grow their own food. So, NASA has been experimenting with hydroponics, aeroponics, and LED grow lights, tech now helping vertical farms use less water and land. It's a taste of the future, brought to you by space travel. The spirit of innovation that drives space exploration also inspires us to think differently about solving problems on Earth. For example, consider the problem of space junk. There are thousands of old satellites and pieces of rocket boosters orbiting Earth. It's a real hazard. Engineers are designing creative ways to clean it up. Nets, harpoons, robots that could grab debris and pull it out of orbit. This kind of thinking, turning a waste product into a solvable engineering challenge, is exactly what we need to tackle pollution on Earth. Now let's think about how we get around in space. Most spacecraft use rocket fuel, which is powerful, but not very sustainable. So, scientists have been developing other ideas like solar sails. A solar sail is a huge, ultra-thin sheet of reflective material. It works like the sail on a boat, but instead of being pushed by the wind, it's pushed by the pressure of sunlight itself. It's a way to travel through the solar system without any fuel at all. This kind of thinking encourages us to harness natural energy sources in new and creative ways. The drive for efficiency in space produces lightweight materials and insulation now used to make cars, planes, and homes more energy efficient. On long missions, you must reuse everything. Lessons that point toward a circular economy on Earth. One of the most important things satellites can do is track the very gases that are causing our climate to change. I'm talking about greenhouse gases, carbon dioxide, methane. These gases are invisible to our eyes, but specialized satellites can see them. Think of it like this. These satellites can watch the planet breathe. They can see where carbon dioxide is being released into the atmosphere. Cities, industrial areas, power plants. And they can see where it's being absorbed. Forests, oceans. It's an extraordinary capability. A great example is NASA's Orbiting Carbon Observatory 2, or OCO2. It was designed to measure carbon dioxide in the atmosphere with incredible detail. It circles the Earth pole to pole, taking hundreds of thousands of measurements every day. The data helps scientists create detailed global maps of carbon dioxide. Those maps show the seasonal cycle, plants breathing in spring and releasing in fall. In 1990, at the request of the astronomer Carl Sagan, the Voyager 1 spacecraft, then billions of miles away, turned its camera around and took one last picture of home. What it saw was a tiny point of light, a single pixel in a vast cosmic sea. Sagan called it the pale blue dot. That image, perhaps more than any other, puts our world into perspective. On that tiny dot is every person you've ever loved, every hero and villain, every joy and every sorrow in human history. It is our only home, and it is fragile. The science we've talked about, the satellites, the data, the spin-off technologies, is all incredibly important. It gives us the knowledge and the tools to protect this pale blue dot. The view from space shows us that our atmosphere is thin and delicate. Our oceans and forests are vast, but not infinite. The challenge of climate change is immense, but we should not feel hopeless. We should feel empowered. We have the ingenuity that took us to the moon. Protecting our pale blue dot is the most important mission of all. Let's get to work, together.